We're now going to talk about some more modern evidence that we have for plate tectonic movement that was not available to Wegener. Most importantly, we're going to focus on seafloor isochrons. In total, we're going to look at 4 pieces of evidence. Number 1, the seafloor is not flat, and I've talked about this in other videos, including the previous lecture tutorial videos. It turns out that seafloor imaging, which really began during World War II in a hunt for submarines, produced a lot of information about the seafloor. And one of those things was that it's not flat. There was a large, giant mountain range in the middle of the Atlantic Ocean. We know now that that's the Mid-Atlantic Ridge. So here's a profile across the Atlantic, and we've got the continental margin, and then the deep ocean basin. Same with Africa, continental margin, deep ocean basin, and then the elevated mid-ocean ridge, which remember is elevated because mantle asthenosphere is welling up underneath it and pushing it upwards. A second piece of evidence is the thickness of sediment on the seafloor. Now in this map, thickness is shown in meters is from dark blue to red. At this intermediate blue color, it's 500 meters of thickness, which is how many kilometers? 1/2. 1,000 meters of thickness is a kilometer. And then we go up to 5, 10, even 20 kilometers. Now, in some cases, the sediment is very thick because there are large river systems draining the continent. Over here, you probably recognize the Gulf of Mexico, and that's where the Mississippi River empties into the Gulf. But let's look in the Atlantic here. This is where the Mid-Atlantic Ridge would be. And what you can see is that sediment is very thin in the middle of the ocean, and as you go further away from the middle, it gets thicker and thicker in both directions. Same with up here. And that's because this mid-ocean ridge crust is pretty new. It hasn't had a lot of time for sediment to accumulate on it. On the other hand, these two continents drifted apart about 180 million years ago, and so now they've had 180 million years of time to accumulate sediment. So the thickness of sediment increasing away from mid-ocean ridges is an important piece of evidence for seafloor spreading. A third one has to do with the isochrons, and this is shown in this picture. Now this is the same seafloor, but now we've stripped away the sediment and we're looking at the age of the crust that's formed during seafloor spreading. And the age is listed as red for new, up to blue for old. So it's kind of the opposite color scheme as the last one. You can see the Mid-Atlantic Ridge here, youngest in the middle, older as you move away, and that makes sense because seafloor comes up and spreads to the side. Here's the East Pacific Rise or East Pacific Ridge, which is also an active spreading ridge. Here are some other ridges. Here's the Mid-Indian Ridge, Southeast Indian Ridge, Southwest Indian Ridge. So you can see the age of the seafloor increases as you move away from the ocean ridge, and that makes perfect sense for seafloor spreading. Notice that the oldest crust that we have in the ocean, out here in the Western Pacific going into the Mariana Trench, happens to be only about 180 million years old. And that's because older ocean crust has been subducted away. Remember, that's very young compared to continental crust, which is billions of years old. A definition of isochrons is given here. It's basically the name for these colored bands where the seafloor is the same age. So for example, we could have the 120 million year isochron, which would be the green isochrons, and you'd see them in various places. Number 4. This brings up the topic of paleomagnetism. Paleo means ancient, magnetism means the force of magnetism. And so paleomagnetism is actually the study of Earth's ancient magnetic field. And the only reason we have information about it is because that ancient magnetic field is preserved in rocks. It confirms seafloor spreading, and it also provides confirmation that the continents have indeed moved. So how do we know we have a magnetic field? Well, you can take a compass outside and it will point north. Your compass needle is basically a little magnet. So here's a bar magnet, sometimes we call that a dipole magnet, and somebody has spread some metal filings on it to kind of show the invisible magnetic field, right? Because magnets have a magnetic field associated with them, but we can't see it. Just like gravity doesn't have strings attached to things falling, it's an invisible force. So this shows how the metal filings are following the magnetic field lines. And it's very similar to Earth's magnetic field when we measure it. And that's why, unfortunately, many textbooks show you a bar magnet in the middle of the Earth. But there are no bar magnets in the middle of the Earth. The only reason they show you that is because the Earth's magnetic field behaves like a dipole. Now, there are other things like quadrupoles and octopoles, and the Earth's field doesn't behave like that, thank goodness. You probably recall that the reason we have a magnetic field is because of the flow of electrons in the outer core. The liquid outer core has electrons flowing through it, and when electrons move, they produce a magnetic field. Some rocks can record the directions of the Earth's magnetic field, as I said, and volcanic rocks are the easiest ones to understand. So here we have a volcano erupting, and these little arrows are indicating the magnetic minerals that are in that lava. And when they're very hot, they just randomize in their direction. They don't point anywhere in particular. There's no net magnetic direction. The Earth's dipole field in this particular picture is shown here. But as those rocks cool, those magnetic minerals eventually solidify and line up to the Earth's dipole field. So if we can go in and get those rocks and measure them, we can figure out, for example, where the ancient North Pole was at the time these rocks formed. There's another really important thing we can figure out from paleomagnetism, and that's paleolatitude. Remember, latitude is your distance north or south of the equator. Paleolatitude can be determined by looking at rocks and the magnetic minerals preserved in them. And the reason is that not only does your compass point north, but if it could rotate in this direction, it would actually point down into the north in the northern hemisphere and up into the north in the southern hemisphere, because the compass would actually be lining up with the magnetic force lines. So at the magnetic North Pole, it would be pointing straight down. At the magnetic equator, it would be parallel. And then south of the equator, it would point up. So it's always going to point north. Now this might be a little bit tricky to understand with this diagram. You're probably thinking to yourself, I don't have this diagram. So let's draw something similar. Draw the Earth, and then draw a few of these lines that are created by the magnetic field. And remember with arrows that things are going to go pointing to the north from the south. So the magnetic direction is along this line. We'll add a few more. And now let's get out our compass. So if our compass were on the North Pole and it was able to rotate in every direction, it would point straight down. In the South Pole, it would point straight up. And remember, this is up for people that are standing down there. As you go lower in latitude, the angle of your compass needle, and by analogy, the magnetic minerals in the rock, are no longer perpendicular to the surface, but they're at an angle to the surface. That's called inclination. And when the rocks preserve this, it tells us what latitude they were at in the past. So for example, how do we know that India was south of the equator when Pangaea existed? Because the rocks in India tell us that it was south of the equator based on the magnetic minerals. So this is a very powerful tool. What I have here is a plastic gizmo that has all these little things on pins, these little iron things on pins, and they're all randomly oriented. I'm trying to mess them up. And what I'm going to do is I'm going to put a dipole magnet in the middle, and you're going to see how all of these wind up lining up with that invisible dipole field. So here's my magnet, and here we go. And now you can see that all of those little pieces of metal have lined up with the invisible field of the dipole magnet. And that is what the rocks will record depending on where they're located on Earth. Another thing that paleomagnetism tells us about is the position of the ancient North Pole. And this brings us to something called apparent polar wander. If you take a look at this map over here, we're looking down on the North Pole. If we measure the magnetic direction of rocks from today, such as lava coming out of Hawaii, the magnetic direction would point to the North Pole. If we measured rocks from 50 million years ago, it turns out the North Pole is over here. And by the way, North America is over here. This is a label for this red curve. If we went back in time to 100 million years, the North Pole seems to be over here. And we go back in time and we see this pathway, or this apparent wandering of the pole from the rocks in North America. Now let's do the same thing in Europe, which is over here, and this blue curve is labeled Europe. Today, if we went to Mount Etna, where lava is coming out, it would show us that magnetic direction points to the North Pole. But in the past, this is the pathway that the pole appears to make from rocks in Europe. Now this suggests, for example, that 300 million years ago, we had two North Poles that were separated by thousands of miles. And this is simply not true. Now this right here is the Atlantic Ocean. If we close the Atlantic Ocean to be in the Pangea configuration, those two wandering paths fall right on top of each other. So apparent polar wander paths support the idea that the continents have moved. Not a fixed continent with a wandering pole, but a fixed pole with a drifting continent. I'm going to finish this up in another video, and we'll talk quickly about magnetic reversals.